In this video, we'll briefly discuss the notion of a set, and we'll also use truth tables to determine whether sets of propositions are jointly satisfiable. The idea of a set isn't really very complicated, but it can be very easily confused, so it's worth a quick peek. We're actually going to take a lot closer view of what a set is further along in the course. So if this doesn't answer all of your questions, just stay tuned, we'll get to more. But the idea of a set is typically defined as a collection of objects, and where the objects are defined, or we use the word members, right, to refer to these objects that are collected. But really the big point about sets, I think, that is important for you to know that could be confused is not so much what a set is, but what a set isn't. A set isn't anything else but those members. That's all the set is, right? So in other words, it's nothing over and above the members that make it up. That's what the set is. So a quick visualization here, quick illustration. My favorite team is the Los Angeles Lakers. And right now, the Lakers are made up of LeBron James, Anthony Davis, Kyle Kuzma, and they have 12 members on the team, 12 players on the team. And I might ask the question, so what exactly constitutes the Los Angeles Lakers? And let's say the Los Angeles Lakers team, not organization, because they have general managers, they have stadiums and stuff like that. But let's say we're just considering the team itself. What constitutes the team? And one answer we might have is just those 12 players. That's exactly what the team is. It is hard to see, like, if you think about, what is the team, it's hard to see what we could point to that would be anything other than those 12 players, right? So that might be an answer that we give. But if that's the answer we give, the team that I grew up watching was Magic Johnson, Michael Cooper, AC Green, and those are 12 totally distinct players from the 12 we have right now. So if we define the team Lakers as just the 12 people that make it up, then it seems like since there's nothing in common between the 12 we have now and the 12 we had back then, that these aren't the same teams. And worse, there are 16 championships for the Lakers team. If we're going to define that team as just those 12 guys, well, anytime I swap out one guy with another guy, I have a different 12 players. I have 11 that are the same, but I have a new one, right? So if all the team is just those 12 guys, then I don't have those 12 guys anymore. I have a different collection of guys. So it's difficult because you think, like, well, how is it possible then to have the NBA, you change at least one player every single year. How can the same team win more than one championships? Seems like possibly they couldn't. Now, I'm not saying that they can't. The reason I bring this up is not to solve this problem. Really, it's not to argue one way or another at all. I don't want to claim that it's impossible to have the same team twice, even if you just switch one player. That's not the point of this. But really, the point of it is to show you what a set is. So when we're looking at the team as just a collection of 12 people, that you change one guy out and put a different guy in, and all of a sudden, it's not the same collection. So we were defining it as that collection, so it's not the same thing. That would be the idea of a set of 12 players, and all the set is those 12 players. So if you swap out one guy for another guy, you have a different set. That's what a set is. Now, today, we're going to be considering sets of propositions. So, in other words, collections of propositions. But it's nothing fancy that we're doing here. Really, all we're doing is considering this particular combination of propositions versus that particular. And if we swap out one proposition for another one, we have a different set of propositions. But all we mean by that is a different combination of propositions. I guess one more thing that you would want to know about sets is that it doesn't matter what order they come in. Like you could have on those 12 players, you could consider LeBron James first, Anthony Davis second, or you could consider, Danny Green first, and then Kyle Kuzma second. You could do any kind of order that you want. We will ultimately be concerned with having a conclusion that's different than the propositions, but that's coming later. Right now, we're just considering them as sets of propositions. Now, the way we denote a set is to have those little curly brackets that I never remember what their name is. And then you list out the names of the members of the set inside of it, separate them all with commas. So let's say I had 3 propositions, P, Q, and R, where P would be, Paul eats pineapples, Q is quails are from Quebec, and R is Randy likes robots. then P, Q, and R would be put into those little curly brackets separated with commas. And again, don't forget that order doesn't matter. So if I were to write the same kind of nomenclature and had R, Q, P, that would be the exact same set as PQR. Now we've already seen the idea of satisfiability. First, we talked about one proposition being satisfiable when it had at least one row on the truth table where it came out true. Then we talked about two propositions and we said that they were jointly satisfiable when there was at least one row where they both come out true on that specific row. Now the idea of a satisfiable set is just going to extend that concept there. So imagine doing more than two propositions all together, and we're looking at all the rows, and there's at least one row where every single proposition in that set comes out true, then that is a satisfiable set. Now notice, if given that definition, it's actually the case that joint satisfiability and just individual satisfiability are kind of like sub-concepts here of the concept of set satisfiability. What do I mean by that? A set can have any number of members. So our set could just have two propositions in it, in which case we'd be talking about joint satisfiability, but that would also be set satisfiability as well if you got that joint satisfiability. But we define that word joint satisfiability really dealing with two propositions. And then individual satisfiability, you know, the single proposition being satisfiable, well, a set could also include just one proposition. So given that, you know, one proposition, if there's one row at least where that one proposition comes out true, then it's the case that all the propositions in our set here have come out true on that one row, but it just happens to be the case that we only have one proposition in that set. So really, that individual satisfiability is the same thing as our set satisfiability. So when dealing with sets, we're going to be asking the question, are these sets satisfiable sets? We'll do our truth tables for all the propositions in our set, and we'll look and see if there's at least one row where they all come out true. So we're pretty much going to be doing the same thing that we've done in the past couple of videos, or something very similar that we've done. So let's go ahead and check out 4.4.1 exercises. Our first set of propositions is number one, P or Q. It's not the case that P and Q, and then our third proposition is P. So one thing we'll do is set up a truth table here where we've listed, again, the P and the Q, the different simple propositions that go into making up our propositions throughout this truth table. One thing we haven't done so far, I haven't been dropping the parentheses, even though I said that was an abbreviation that we were going to start to adopt. And we also haven't adopted dropping the parentheses when we're stringing rows of ands and ors together. So today I thought we'd go ahead and check that out just so you get a feel for what that looks like. Looking at proposition one, P or Q means that at least one of those two things is going to be true. It looks like on proposition 3, it says that P is true. So I know that, you know, P or Q and P can both be true at the same time because, you know, P will just be that one that's true. And then proposition 2 says it's not the case that you have both P and Q. What that means is you can't have both of them. At least one of those is going to be false. So if Q were the one that were false, you could have P be true, and that would be just what proposition 3 says, and that would make proposition 1 true too. So it seems like these will be jointly satisfiable when P is true and Q is false. But let's go ahead and distribute our truth values. Our first proposition here is P or Q. Only false when both disjuncts are false. That happens in row 4. The rest of the rows are true. Then we'll have to do proposition 2, the conjunction there first. Only true when both conjuncts are true. That happens in row 1. The rest of them are false. But we're negating that. So we're going to have to flip the F's and T's. And now row 1 is the only place where it's false. The rest of the propositions are true. The rest of the rows are true. And then P, now I told you before, Nicholas Smith, our author, said that we can forego writing a separate column for simple propositions because in the key over here on the left-hand side, we've already sort of covered those. I'm going to throw it on there anyway just because, I don't know, I like to make sure I got everything straight. And I look at it and I see, P is true in the first 2 rows, false in the second 2 rows, or the 3 and 4, row 3, 4, or row 3 and 4. So it looks like in row 2, they all come out true. And again, that's where P is true and Q is false. The set for number 2 is proposition 1. It's not the case that if P then Q. Proposition 2 is P if and only if Q. And proposition 3 is not P or Q. So let's evaluate it real quick. That first proposition, it's not the case that if P then Q. Since a conditional is only false when you have a true antecedent, false consequent, and we're negating that conditional, that negation is only going to be true when we have that P is true and Q is false. And it looks like if P if and only if Q, that second proposition right there, is saying that if you have P, you have to have Q, and so if you don't have P, you can't have Q, and vice versa. So it looks like those two propositions are not going to be jointly satisfiable. Then it doesn't matter what proposition 3 is, because that won't be jointly satisfiable as a set. So doing number 1, let's go ahead and build if P then Q. Again, only false in row 2, where you have a true antecedent, false consequent. Then we're going to negate that. So we're going to flip all the F's and T's. It's only true now in row 2. And then the P if and only if Q, it's going to be true when P and Q are both true, or P and Q are both false. So row 1 and 4. Otherwise, it's going to be false. Sure enough, it looks like proposition 1 is only true in row 2. Proposition 2 is not true in row 2, so they never meet up. But let's just do the third one for fun. Not P or Q. First, we have to build up that not P, so that flips the F's and T's. Now P is true only in row 3 and 4. The disjunction is only false when both disjuncts are false, and it looks like that happens in row 2. Otherwise, it is true. But in any case, we already know that this is not a satisfiable set. Problem 3 gives me the set. First proposition, if P, then not P. Second proposition, either P or not P. Third proposition, if not P, then P. Now, P or not P, I know, is always going to be true, right? That is the principle of bivalence. So we've already talked about that in previous videos. You have to have P or not P. You can't have, a third option here. You have to be at least one or the other in classical logic. So that one's always going to be true. But then when I look at that if P, then not P, so if P were true, I would have not P. That's a contradiction. You can't have that, right? So that one, if you had P, you'd have a problem because it would give you not P. So in other words, P can't be true. You can't have that. But then I look at that proposition 3, and it says if you have not P, that's going to give you P. Well, now we have a problem, right? Because P can't be true or else I'd have a contradiction. P can't be false or else I have a contradiction. So it looks like propositions 1 and 3 should not be jointly satisfiable. They should be jointly unsatisfiable, where even though proposition 2 is a tautology, it's always true, that's not going to matter. You're never going to have one row where they all come out true. So let's see, let's build these out. So I distribute all the T's and F's, and in proposition 1, first we have to build that not P, right? And that flips the T's and F's. The conditional now is only false when you have a true antecedent and a false consequent. And it looks like that happens in row 1. So row 1 is false, row 2 is true. Then in proposition 2, again, that not P, we're gonna have to build that first. It flips the T's and F's. P or not P is true when at least one disjunct, possibly both, are true. Only false when both disjuncts are false, but we see here that that never happens, so this is always true. And then in proposition 3, again, we have to build the not P first. A conditional, remember, is only false when you have a true antecedent, false consequent, so it looks like that happens in row 2. So this is false in row 2, true in row 1, and I see now that there's never a row where all 3 propositions come out true, so this is unsatisfiable set. For problem 4, we now have a 4 proposition set. Our first proposition is P or Q or R. Our second proposition is if not P, then not Q. Our third proposition, if not Q, then not R. And our fourth proposition, not P. So I've built a truth table here, and notice I have taken away the parentheses for proposition 1 because we said that we were allowed to do that for a string of disjunctions. So a quick evaluation of this, proposition 4 and proposition 2 are going to combine to give us not Q, right? If not P, then not Q. Proposition 4 is not P, so we're going to have not Q. And that not Q with proposition 3 is going to give us not R, right? Not Q, then not R. We have not Q now, so not R. So if proposition 4 is true, then we're gonna have to have not R be true. And then I look over at that P or Q or R, oh man, but then remember also not Q has gotta be true too, right? Because that not P gives us not Q. So if not P, if proposition 4 is true, not P, that's gonna give us not Q and not R true as well. But P or Q or R is demanding that at least one of those things, right? We have at least P or Q or R, and it looks like we can't have any of those things. So it looks like proposition 1 is going to spoil the party here. We're going to have an unsatisfiable set because proposition 1 doesn't play well with the rest of the propositions. But let's go ahead and distribute our T's and F's. P or Q or R only false when you have all three of those propositions false, and that happens in row 8. Otherwise, it's true. If not P, then not Q. Again, we're gonna have to build those negations first, and a negation flips the T's and F's. And then the conditional only false when we have a true antecedent and a false consequent, otherwise it's true. Same thing happens with that if not Q, then not R. We have to build those nots first, right, those negations. That's just a matter of flipping T's and F's. And then finally the conditional only false when we have a true antecedent, false consequent, otherwise it's true. And finally, proposition 4, we have that not P, so it's just that negation there is just gonna flip the T's and F's. Now, looking at our truth table, the only place where proposition 1 is false is in row 8. So it looks like we have good chances here, but that's also the only place where we have propositions 2, 3, and 4 all true together. So it looks like we do not have a satisfiable set, we have an unsatisfiable set. My set for problem number 5 is this: P if and only if Q, that's proposition 1, proposition 2, Q or R, and then proposition 3, if R, then P, and it definitely looks like this is gonna be a satisfiable set. If R is true, that's gonna make P true in proposition 3. P being true is gonna make Q true in proposition 1. And then Q or R will be true by that Q and that R. So there, I know there's going to be at least one place where these are all three propositions are all true. So let's distribute the T's and F's. And P if and only if Q is only true when you have P and Q both true or P and Q both false. And that looks like it happens in rows 1, 2, and then 7 and 8. Q or R only false when both disjuncts are false. And that looks like that happens in row 8 and row 4. And then if R, then P, only false when R is true and P is false. It looks like that happens in rows 5 and 7. And then sure enough, row 1 is the first row there, and all three of them are true in that row. So I don't have to look any further. I know this is a satisfiable set. Problem number 6, first proposition, if not P, then not Q. Proposition 2, P if and only if Q. Proposition 3 is P. So I know for proposition 3 to be true, P just has to be true. If I'm going to make that jointly satisfiable with proposition 2, P if and only if Q, that would mean that Q would have to be true. And if P is true and Q is true, that's not actually going to affect that if not P, then not Q. That could still be true when P is true and Q is true. The only way that this can not be true is if that not P turned out to be true and not Q turned out to be false, but it doesn't look like we have that in that situation. So it looks like this will be a satisfiable set. Let's go ahead and distribute the T's and F's, and we'll build those negations there in proposition 1, and then we will do the conditional only false when you have a true antecedent and a false consequent. And it looks like that happens in row 3. P if and only if Q, only true when you have P and Q both true or P and Q both false, and that happens in rows 1 and 4. And then P is true in row 1 and 2, and it looks like we have all three propositions true in row 1, so a satisfiable set. Problem 7, the set is this: proposition 1 is not P. Proposition 2, if P then P. And then proposition 3, not P if and only if P. Now, not P if and only if P, I already know is going to be a contradiction. A biconditional is only true when both propositions that make it up are true or both propositions that make it up are false, but not P and P cannot be true together and they cannot be false together. So this is a contradiction. One contradiction in your set here, and you'll never have a row where all three propositions turn out to be true, so you'll never have a satisfiable set. But let's distribute the T's and F's, and in proposition 1, the negation there, we're gonna have to flip the T's and F's. So it looks like not P is true in row 2 now. Proposition 2, if P then P. Actually, I missed this. This is a tautology because you can never have the antecedent be true and the consequent false because the antecedent and the consequent are both P. But let's build first the first conditional. Again, only false when you have a true antecedent, false consequent. That never happens. And so that's always true. And then we look at the bigger conditional. Again, only false when you have true antecedent and false consequent. But you never have a false consequent here, right? So then this is always going to be true. And then finally, not P, if and only if P, we have to build the negation first. So it looks like that swaps the F's and the T's. And this biconditional is only true when you have both propositions true or both propositions false, and that never happens. So this is always false. We have an unsatisfiable set. Problem 8, the set is P or not Q. If P, then R, not R, and then if not R, then Q. So 4 proposition set. And let's see here, for proposition 3 to be true, R has to be false, right? Not R won't be true. And that will make Q true for proposition 4 if those two are going to be true together, right? So if Q is going to be true, looking at proposition 1, P or not Q, right? That means at least one of those two things are true. And if I just said Q is true, that means not Q can't be true, right? So P is going to have to be true for proposition 1 to be true. And if P is true, then proposition 2 says that R will have to be true. But then I look at that not R in proposition 3, and we said not R there, so that would lead to a contradiction. So this will be an unsatisfiable set. Let's go ahead and distribute the T's and F's, and we'll have to build that not Q in proposition 1 first. That flips all the T's and the F's. And then P or not Q, only false when you have both disjuncts false. And it looks like that happens in rows 5 and 6. If P then R, only false when you have P true and R false. Looks like that happens in row 2 and row 4. Not R flips the T's and F's, right? So they're peppered throughout there. I'm not going to go through each one of them. And if not R, then Q. Again, that not R, we're going to switch the T's and F's. And if not R, then Q. Only false when not R is true and Q is false. Otherwise, it's true. And I look at every single row, and sure enough, there's never a row where all 4 propositions turn out to be true. Problem 9, not R is proposition 1. Proposition 2 is not P. Proposition 3 is if Q, then not Q, then R. So let's see if we can make sense out of this. That not P, notice, has nothing to do with the other propositions. So that's actually not going to be a problem at all. But let's see, if not R is true, right? So in other words, R is going to have to be false. That would mean in order for proposition 3 to be true, then you couldn't have if Q, then not Q be true, because then you'd have a true antecedent and a false consequent. And so you'd have to have a Q, if Q, then not Q, false. And that shouldn't be any trouble. So it looks like that this will come out to be a satisfiable set. We'll distribute the T's and F's. For the not R in proposition 1, we flip the T's and F's. For the not P, we do the same thing, flip the T's and F's. For proposition 3, we're going to have to build up that not Q first. So that flips T's and F's, right? And then the if Q, then not Q, only false when the antecedent is true and the consequent is false. That's actually going to happen every single time the antecedent is true. You're going to have a false consequent on this one. So that's rows 1, 2, 5, and 6. And then if Q, then not Q, then R, that's only going to be false when you have a true antecedent, false consequent. So when if Q, then not Q is true and R is false. And there will be some places where that happens, it looks like. But there are also rows where all 3 of these guys come out true. So this is a satisfiable set. And finally, problem 10, either not P or not Q. Proposition 2, it's not the case that P and not Q. Proposition 3, P or not Q. Proposition 4, it's not the case that not P and not Q. So let's try to deduce here what we think is going to happen. Proposition 1 and proposition 3 are interesting because proposition 1 says either not P or not Q is going to be true. Proposition 3 says P or not Q is going to be true. So, not P and P can't both be true at the same time. So for one of those disjunctions, the P or the not P is going to be false. And you're going to be left with that not Q. That not Q is going to have to be true. So we know not Q is going to have to be true if those two propositions are true. Proposition 2 says it can't be the case that you have both P and not Q, but we already said not Q is going to have to be true, so it must mean that you can't have P. In other words, not P, right? P's got to be false. And then proposition 4 says it can't be the case that you have both not P and not Q. Uh-oh, we have a problem here, right? We just saw that we have to have both not P and not Q, but proposition 4 says you can't have that. So these 4 propositions won't be a satisfiable set. Let's go ahead and distribute our T's and F's. And then in not P or not Q, the nots will flip the T's and the F's, and the disjunction will only be false when you have both disjuncts false, and that happens in row 1. And then not P and not Q, first we'll have to build the not Q, again flip T's and F's. Then we'll have to build that conjunction only true when both conjuncts are true, and it looks like that happens in row 2. And then the negation flips the T's and F's. So it looks like row 2 is actually now the only place where it's false. And then P or not Q, we'll have to build a not Q first, flip T's and F's. The disjunction is only false when both disjuncts are false. Looks like that happens in row 3, otherwise it's true. For the last one, we have to build the not P first, and then the not Q also, again, only flip T's and F's. Then we'll have to build that conjunction only true when both conjuncts are true. That only happens in row 4. And then the negation there flips all the T's and F's, so that actually becomes the only place where that's true. And now I look at this and I say, wow, there's never a row where all 4 of these propositions come out true. So this is not a satisfiable set. This is an unsatisfiable set. That is all we have for sets of propositions. For next time, please go ahead and read 4.5, which is more on validity. And that's going to be the last part of chapter 4, and we'll be moving into chapter 5 after that. I'll see you in the next video.